Hi everyone, welcome back to the channel. So let's solve a real complex problem here. This is not so easy to solve, although the solution is simple and the path to solution is also very simple, but it's very difficult to understand how to get around with this problem. And this is the kind of problem that Jaish has been asking. So watch the video carefully, and there are few things for you to learn to solve such problems. Okay, so let's get into the problem. A water turbine consists of a large number of paddles. So think of these blades as the turbine blades, okay? And with some fixed length. So assume that these blades have some fixed area, okay? So typically these blades are going to be like this, okay? Like this, okay? Individual blades. And these are attached to, let's say, some internal, there is a drum inside which is like a cylindrical drum, and the blades are attached to, let's say, these drums, okay, like this, something like this. Imaginary cylinder, it's given that this all are co-axial, okay. A stream of water with velocity v and flow rate mu is directed on the turbine in such a way that it hits the paddle near the perimeter. So this is where the water is hitting, okay. Find the maximum possible usable power that could be extracted from the turbine. Okay. How do we approach this problem, right? So let's first logically analyze. As I always say, before you solve complex problems, think for 10 seconds, 15 seconds, what's going on. So if you think, if let's say this turbine is initially stationary, it's not moving, let's say, and these are blades, okay. Then once the water starts falling on it, the turbine will start rotating like this, right? Now, when the turbine starts rotating and the blade starts moving with some velocity, then since the water is coming with, let's say, mu kg per second, so when it is stationary, it will receive some amount of water, and when it is moving, it will receive some different amount of water. Especially when you try to compute the force because of the relative velocity between the flow of water and the speed of the blade. Okay. Now here there are two major things to consider. Okay. So the one part is that is the jet feeding the turbine, which means throwing the water at the turbine using a fixed mass flow supply, okay, which is a fixed mass flow supply. Okay. So what does this mean? This means that irrespective of how the blades are moving and whatever speed at which blades are moving, these jets are actually providing a constant fixed mass, okay, all the time. So this is one part. Or there could be, so, or is the area, or you can call geometry also, of the blade or paddle fixed so that the intercepted mass flow varies. So this is a clear distinction that we need to get. Okay, this question is not talking about either. So what we will do, we will solve eventually for both of these options. But if you get questions, let's say in your exam or JE, they will specifically mention whether this is true or this one is true. Okay. In a real world scenario, this is true. This is a real world scenario. Okay. So you would have seen such turbine, and it follows this model because this is when the blades start moving, then the amount of water that it should receive because of the flow from this jet is going to be dependent upon the velocity of the blade itself. Okay, and we will see that why. Okay, so let's solve the problem for, let's say, case 1. Okay, And case 1 is where jet is feeding the turbine with fixed flow of supply. Okay, so mu is fixed. So we know that the force that is acting at the blade is actually the mu times the relative velocity, right? Relative velocity at which the water is falling. Relative velocity is important here because imagine this is the blade and this is at rest right now. Okay, so let's say the blade velocity is equal to u. Okay, so right now let's say this point u is 0 and the stream of water is coming with velocity v. So in this case the entire v velocity will hit this blade or the paddle. But in some other case, when this is moving with some u greater than 0 and this is coming up with v, then the approach velocity is actually v relative, right? Which is going to be v minus u, right? So therefore, the F will be mu v minus u, okay? And power, as we know, is F into u because u is the velocity of blade. So that's the power that is being generated. And this will become mu v minus u u. Okay, and to maximize power, we need to just differentiate with u. We need to find at what u this power is maximum. And this is going to be 0 minus 1 u plus, and this if we put 0, we get u as v by 2. Okay, so at this velocity, the maximum power could be generated and the power would be mu v square by 4. So this is a simple answer and is simple to solve for case 1, which is a very limited scenario. It's not a realistic scenario. Here we are assuming that the flow of the water is totally going to be consumed by the blade at any velocity of the blade. Okay? That's not correct. What realistic is that the area of the blade is fixed. So the fixed amount of area will get that much of water, okay, on it. So we need to consider that. So which means that for case 2, okay, we again start with same F equal to mu v relative, and this is mu. Let's say instead of mu, we call it mu u. Okay, I'll tell you why. This is v minus u. And mu u is the flow at any given u. Okay, and we don't know that. So we'll have to consider mu u. And what is mu u if you see? So mu u is how much water is hitting the, let's say, this surface area of the blade of the paddle. So if let's say surface area is S, then the water that is hitting it is the relative velocity of the water, okay, relative to the speed of the blade, okay, and then let's say the density of water is rho. So then mu u will simply become rho S v minus u, okay, and when u is 0, then we get mu u as rho SV, which is the initial mu. So when u is 0, then mu u is simply mu, which is given. Okay. So then the F becomes rho S v minus u square. And the power is again F into u, right? So rho S v minus u whole square u. Okay. And then to maximize the power, we again differentiate this with u, and this becomes 2v minus u minus 1 u plus rho S v minus u square into 1. And this we put to 0. Now there are two answers here. The first one is that we get u as 0, and the second one is u as v by 3. Here we get u as v by 2, right? And u is 0 is correct because that time the power is minimum. If you check again, differentiate, you will get power is minimum here. And the power will be maximum at this point. And this is true also when the turbine is not moving, it is generating 0 power, right? So u is v by 3. At this speed of the turbine, it will generate maximum power. Okay, and then the power will be rho s. This is 2v by 3 square into v by 3. It is rho s v cube, and this is 4 by 27. And we already know that mu is nothing but rho sv, right, when u is 0. So the power will be mu 4 by 27 mu v square. And this is the power that a turbine can produce optimally if the turbine moves with v by 3 velocity, compared to v square by 4 here, which is not realistic. The actual value is mu v square into 4 by 27, and that's the answer. Okay. So please do send me your comments and questions if you have any question here or anywhere else. If you want me to solve a particular problem, please do send me across that problem. You can send me an email or just leave a comment there. And if you like the video, please do subscribe to the video, like it, and share it with your friends. Okay, thank you very much. Thanks for watching. Subscribe and gain access to concepts and tips for doing better in IIT, JEE or other examinations. Keep up the great work.